Bismillah ar-Rahman ar-Rahim. Good afternoon, everyone. Today I will start to summarize my study to last 2 years when I was working to doping perovskite oxide. Like in one source, when the research said by doping, by using some element doping, we can increase the properties, electric and magnetic properties to the structure. I used calcium and strontium as element doping. Let me start with the first slide, which can illustrate my result, which element was good, that was better, and why. Bismillah. Content, I focused on research gap when I noted some weakness in the previous research. By that, I written my research gap, scope, or can say object, methodology, result, conclusion. Last, the points were dependent on my thesis. I take all the important information, results, conclusion, all of these were from my results, from my thesis. Now, at the research gap, I focused on 2 points. At first, I focused on the impurity, just like the mine structure, because the previous research focused on the mine structure more than the impurity. And last point was I take more than 1 molar ratio because the previous research focused on almost on 10 molar ratio, because that I wanted to test is just 10 molar ratio is the best or not by taking another 2 molar ratio. It where they are 1, 5, and 10 molar ratio. Sorry. Now let's talk a little bit about the object, what I prepared. Actually, I prepared 3 grams from all the lanthanum, calcium, manganese oxide, and strontium and manganese oxide, lanthanum, strontium, manganese oxide. Like we know, the molar ratio between the calcium and lanthanum must be 1, because that when I select lanthanum to be 0.67, that means the element doping molar ratio will be 0.33. I depend on the, how I can say, the undoped lanthanum oxide, that means lanthanum manganese oxide. We selected the transition element be manganese because it's interesting and it has a unique property. It was the, can say, the double exchange, because manganese, it has more than 2 ionic number. I will illustrate all of these at next slides. Like is written there, lanthanum manganese oxide, like written in source 78, antiferromagnetic and isolated with white temperature. By doping in it, I try to increase the electric and magnetic properties to this structure. That means I try to make it be ferromagnetic and conductor, okay, by somehow. Now, I focused on this doped function. We can say, or let me not, don't forget this important line, doping employed to increase the ferromagnetic properties, like I said before. We focused on the salt gel. It's a chemical process to produce my perovskite with controlling on sintering temperature. All of these 2 important things to enhance the microstructure, electric and magnetic properties to my structures. 3 grams from all of them. Now let's take a look to undoped perovskite oxide. the general perovskite, it's a cubic, it's n-doped crystal structure AbO3. A in my topic was lanthanum, B's transition element here, it was manganite, and I said why we selected it, and 3 atoms of oxygen. After doping it, the crystal structure will distorted. We will see another crystal structure. Lattice parameters will change a little bit, or all of them, or one of them. Okay, here lanthanum is it's lanthanum, and it's a rare earth, one of the rare earth elements. B, or let me say the doping element, calcium or strontium, all of these belong to alkaline earth. Okay, now let me talk a little bit salt gel method. It's a chemical method. We have 3 kinds of salt gel: alkoxide salt, alkoxide, and bechany. I focused on alkoxide, okay, alkoxide salts, sorry. Let me say why I selected it, because it has many advantages: pure uniformity, full control on the particle size from 10 to can reach 100 nanometer. It's a huge increasing, environmentally friendly. It's not toxic, not totally not toxic. We must be careful when use this method, but we can say it's environmentally friendly, easier, and can say it can be with less temperature, with less than 220, easily to scale up. And like any method in our life, it has another side. The side is the disadvantage. The most too important thing is in salt gel method is the high sensitivity to moisture, because that I used foil aluminum, okay, to protect my perovskite powder, and creating fractures when at the third step, the drying, because that I use the gelating agent, okay, and how to scale up multiple steps and time, okay. Here, from this diagram illustrates to us how the using number of salt gel is increased from 20 current to 2020. It's more than 1,500 times, because that's why, because it's very interesting method by produce pure uniformity, full control, like I said before. Now let's go a little bit deeply to the 5 steps of the salt gel. The first one was hydrolysis, second condensation, drying, aging, calcination, okay? After calcination, I will deal with the aerogel, will be like that. After that, the final product by using that's mean until here the salt gel method is done. And after that, I will illustrate what is the black powder here and how we could do it. Let's start from hydrolysis. At hydrolysis, it's precursors. It's inorganic metallic oxide plus inorganic solvents plus the chemical agents or gelating agent, sorry, is the citric acid and ethylene glycol. Here, let me come back to the precursors: lanthanum oxide, centratium nitride hexohydrate, calcium nitrate hexohydrate, manganite nitrate hexohydrate. I used all of these as precursors to know how much I need to all of them. Maybe I spend the semester to can clearly calculate each one, how much gram I need from all of these precursors. I used the scalar. I was here scaling it to depending on my column, my calculations. Okay. After that, inorganic solvents, it was a pure water. Actually, I put it approximately, no, definitely I put it 50 millimeter, and after that 25 hydrochloric acid. All of these, put it in this glass, and at last the gelating agent, citric acid and ethylene glycol. Here's important note: homogeneity is limited by the presence of water, because that know how much I must put in this tube. It was very important. We will put it just 50 millimeter, not more, not less. Here, citric acid and ethylene glycol as a gelating agent were with different molar ratio, like I illustrated in the research gap. Okay. The research gap, I used 3 different molar ratio, 1, 5, 10, like I said before. To avoid the cracks, and I will illustrate why the cracks it's happen. Now let's me talk about the second state is condensation. What does mean? That's mean here the sol will be by polymer network made of metal oxide linkage. By that I have a sol now. By putting a magnetic fish here, by using stirrer device to stir the liquid, let me say in the tube, and I put it a magnetic fish to make this stirrer process be the best. And step by step, I increase the temperature from here from 100 to step by step to be 150, 200, 250, something like that. Here, to form gel, that's mean the viscosity is increased. That's mean polar network grows. By that, the porous structure is formed. Okay, viscosity increased. That's mean polymer network grows. By that, porous structure is done. We have porous structure. Which phase? At gel phase. Third step, aging. Gel precipitation network will happen. Some collapse will happen, which decreases the porosity. At gel, I said we have porous. At aging, the porous will decrease, and the thickness will increase that to be something like honey between colloidal particles. At last, increasing temperature, a little bit more, increasing temperature and evaporation process is started by using higher temperature. Why? To evaporate the solvent. I'm talking about now the hydrochloric acid and water, the pure water. Because the difference, why we have cracks in sol agent, in sol gel process? Because a difference in the contraction speed between inside and outside of the gel for the formation of cracks during drying steps. That's mean the main reason to these cracks is the different speed contraction between inside and outside of the gel by increasing the temperature. It's the main reason to the cracks. And I use the aging agent to avoid this disadvantage. When the liquid is removed from the gel, major change to the network structure occurs and extra gel is formed. This think like a foam is named extrogel. That's mean here the sol gel process is done. But here the sol gel process, by using the sol gel process, this structure, this form is not pure yet. Why? Because it's have hydrocertic acid and ethylene glycol. I use the same heating treatment to evaporate all of the certic acid and ethylene glycol by using this furnace, by calcination, by using the furnace to two reasons. First one, drying gels from the chemical agents, like I talked before, certic acid and ethylene glycol, densifying the material to produce crystalline, here my crystalline with different molar ratio, my crystalline. Now I will use the mortar to be sure I have homogeneous mixture. I use this mortar to decrease the grain size and be sure I don't have any possible accumulation. Okay, by after that, when using this mortar is done, I use the pressure to produce bolts with 1 cm diameter and half with thickness. The next step will be dealing with X-ray diffraction device. Like I said before, I use 3 different satanic temperature, 900, 1100, and 1300 in the process. All these bolts with different molar ratio will be inside furnace with these 3 different temperatures. I have just 12 belts at 900 and 1100 because at 1300 my belts is melted, because any solid, any structure has multi-temperature. That's mean I increased it, I passed it. Now let me talk about the X-ray device, X-ray diffraction device. The 12 belts were characterized by X-ray device. This device, it has 3 important parts. First one, the source, X-ray source. Here we putting our belts inside this point, okay, and the detector, the writer, or you can say, I don't know. And this device will route like that, and I will have different picks. Each picks, sharp or bordering pick, has a meaning. Let me talk about that at next slide. Now, a special interference effect. Now, at this X-ray on the atomic plans, these rays will distract. Okay, now I'm talking about 2 important things, and the interference and the diffraction. These are constructive and destructive. The constructive, by this constructive, I will have my picks, okay, from the which tablet I put it, and I put inside the X-ray device. And the destructive, that's mean waves are out of alignment. Let me talk a little bit on to them, to illustrate them. Constructive, that's mean these 2 waves are the same alignment, because that will be multiplied to make this wave be bigger, okay? But when the waves are out of alignment, that's mean I have destructive diffraction, and the wave will be lying like that. Why I have the constructive and destructive interference or destructive diffraction? Because the atomic plan will act as a slide. Okay, this is very important. Now let's take a deeply look. When atomic plants act as a diffraction slide, like I said before, the constructive interference defined by Bragg's law, lambda equal to d sine theta. I have single phase, I have a single wavelength, because that I said lambda equal to d sine theta. Here, wave number one, wave number two, some of them are scattered, incident angle, reflected angle. Here I have from this point to this point d sine theta, from another point d sine theta. That's mean I have here 2d sine theta. The distance between these two atoms, it's a d. Okay, the distance between these two atoms. Here, after taking the result from X-ray diffraction, I used match to calculate the crystal structure to all of these two structures. After that, Rotevelt method, sorry. What is it? What it is, sorry. It's a function in foolproof program to calculate all of the shape, peak shape, unit cell parameter, and the coordinates. The peak shape, unit cell parameters, and coordinates by using Rotevelt method. It's a mathematical process in the software foolproof. To calculate lattice parameters, particle size, and strain, here the foolproof used the Thomson-Cox-Hastings function to refine the, let me say, foolproof used two important functions. First one, Thomson-Cox-Hastings to refine peak shifting, peak bordering, peak shifting and peak bordering. And the second function was Williamson-Hill plot to calculate the particle size to each one, to each peak and strain. By that, could calculate the average to all of these peaks. It's no way to can calculate the average with a huge range of peaks with Schroeder equation or another. But Williamson, Hill plot, and Thomson-Cox-Hastings could do. After that, how I could plot these peaks. I could plot these peaks by using original program. Here, the observation intensity with a black line, with circle, red circle, it was calculation or calculated intensity. Here, the difference between observation and calculation. Here, the peaks at the first line, it was the peaks of the mine structure. After that, the peaks of the impurity. By taking a look to this plot, I know I have one mine structure and one impurity. Here, let's talk about the peak width of the peak depending on what? Depending on the crystallized size and syntonic temperature, lattice strength. Actually, when particle size increase, the peak will be sharper and sharper. And the reverse situation with the strain, when strain increase, the peak will be boarding more and more. Here, I have interesting thing. I have at 900, at 5 and 10, at lanthanum, calcium, manganese oxide, I have one line of peak. What that mean? That means I have single phase. That means I have pure structure without impurity. Maybe because that here I have some noise between the observation and calculated intensity. Here the crystal structure of the impurity, it was lanthanum chloride oxide, and here the mine structure. It's very clear, the manganese O6, it's very important. I focused on them to can know by using Vesta program, sure, to can calculate the distance, the manganese oxygen bond length, and manganese oxygen manganese angle. I will talk all of them at the next slide at results. Okay. Here I have interesting plot. It was the last at Centrentium at 10 and with maximum temperature it was 1100 Celsius. Here I have 3 lines of pics. First one to mine structure, like I said before, and the last 2 lines that act, I have 2 impurities. Okay, all of them it was lanthanum chloride oxide, that's right, but with different crystal system, tetragonal cubic structure. After doping, by depending on my result, all the manganese oxide, oxygen, and manganese oxygen, manganese angle, that's parameters, unit cell volume, particle size, all of these are changed. Okay, let's take a look to these curves. It's easy to illustrate at 1 molar ratio from 900 to 1100 when I increase the temperature to be maximum, I have a exponentially increasing, let me say, from less than 600 to approximately 800 nanometer. At the last, all of these are increased by increasing the temperature, but the less molar ratio, it has the greatest or biggest increasing in particle size with same molar ratio. Here at 10, it has the smallest strain, and that's great. The volume to 10 molar ratio, it was the bigger when increasing the temperature. That's mean at 10 molar ratio, all of the unit cell volume and the strain are the best. Here now, let me talk about lanthanum centratium manganese oxide. Here, at just 2 molar ratio, not at as calcium, it was talking about or working about 3 different molar ratio. Here, just 5 and 10. Actually, centratium, it was difficult, little bit more than calcium when I was working on the match or foolproof. Actually, I am not advised to use centratium like a doping element. It has, from the results, my opinion, it has weak results. That's mean weak properties. Maybe if I did my research again, I was working on barium. Okay, strontium at 10, it has the minimum strain, and that's mean it's wow. That depend, that struggle the 10 molar ratio, because the other research almost most of them say the 10 molar ratio is the best, and at the unit cell volume, all of the 5 and 10 molar ratio, it was maximum when increase the temperature to be 1100. Now let's take about simple conclusion. When increase the lanthanum, strontium, manganese, oxygen 900 to 1100, manganese, oxygen, manganese angle, it's ideal. It's 180. That means it's ideal. It's perfect. It's the best. With all of the molar ratio, it was with all of them, because that I think calcium is better than strontium as a doping element. Bond length of the 10 is increased a little bit. That means at 5 it was better. As the temperature increased, the particle size is grown, but at 1 molar ratio is the bigger at the same temperature, like calcium when I talked on it. Note, let's say it's very important and struggle the 10 molar ratio, and here the 5 molar ratio too. All of these 2 molar ratio at less temperature are without impurities. That means single phase. It's wow. Less temperature, by less temperature, we produced single phase without impurity. Without impurity, that means increasing electrical and magnetic properties. Crystal stress system of impurity is changed from tetragonal to be hexagonal at 1100 Celsius. Now let's talk about the strontium structure. Strontium has doping element, the structure perovskite. As the temperature increased, that's right, the angle is increased and is the biggest, but not like the ideal angle at the strontium, at the calcium, sorry. And is decreased little bit when increase the temperature. Bond length is reduced in 10 molar ratio, and that means it's good to be. Particle size of the perovskite at 5,900 is the biggest. Here at 5, not at 10. That's mean the same situation with the calcium, lanthanum, calcium manganese oxide. The less molar ratio, it has the biggest particle size. And by increasing the temperature is decreased. Particle size at 10 molar ratio with the maximum temperature is decreased, and its impurity too when increase the temperature. That's mean not always by increasing the temperature I can reach better structure. Strain was minimum at 1100 Celsius at 10 molar ratio. It's good noise, but at other less molar ratio has the biggest particle size and at same temperature. At last, it's very important, and you can say, because that I say the strontium, it's not good as the element doping, because element doping, yes, because here at 10 molar ratio and 1100 Celsius, it has 2 impurities. That means 3 phases, because that sure the electric and magnetic properties will decrease. Here, the lanthanum. Now, let me talk about all of them. Lanthanum, calcium, manganese has larger particle size. By that, the better ferroelectricity. Bond angle, lower bond length, increasing the electric and magnetic properties of perovskite. Here, strontium, lanthanum, strontium, manganese oxide at 10 molar ratio, low strain at 1100, and at less than temperature, the biggest angle but the manganese oxygen is the smallest and at last bigger particle size. Here, lanthanum, calcium manganese oxide at 10 and 1100 Celsius is the best ratio. Sure, because one of these advantages was the ideal angle between manganese and oxygen and temperature to synthesize the perovskite with super electric and magnetic properties, and increasing temperature is required to promote the perovskite properties. We know when increasing the temperature, we will give a great opportunity to the crystallite to recrystallization again. We can say 10 molar ratio is the best, but at 1000 Celsius, when I'm talking about the strontium at the doping element. Maybe it has another advantage. It has good quality, but with less temperature. At the higher temperature, it acts with abnormal behavior by producing two impurities instead of one. By all of these results, I can say calcium ideal angle with less strain was better doping element than strain, three phases at 1100 Celsius. I'm talking about the higher synthetic temperature, while low temperature and low molar ratio, we can say produce the worst electrical and magnetic properties. Here, talking about the future work, should focus on the synthesis process. Like I said before, maybe if I prepared my research again, I will work on salt gel, okay, but with pitching. And I think it's interesting because it has less sensitivity with the moisture, okay? That's not need to put maybe foil aluminum to protect my structures. And the doping agent, calcium, maybe I will use barium and synthesize the properties and take a look which one is the better. Additionally, investigating the long-term stability and durability of these materials under various operational conditions will be crucial, sure, for their practical implementation in technological applications. That's it. Thank you about your watching, your listening. Have a good day and see you at next video. When and where, I don't know. Have a good day.